Here we are in our third part of lecture 3, and we're going to talk about rate laws and reaction orders. So we looked at reaction rate and concentration. We know how concentration affects rate, but one of the things that kinetics really tries to do is to establish a mathematical connection between concentration and rate. It's one thing to say that as concentration goes up, rate goes up, and as it goes down, rate goes down. But we want to be able to establish something where if we have a certain concentration, we can actually calculate the rate of a reaction. Now, the reason we might want to do that is we might be involved in some kind of manufacturing process where the faster that we can make a product, the more money we're going to make in a certain amount of time. And so we want to see what is that relationship between concentration and rate so we know what we need to feed in order to get a certain amount of product out at some certain rate. So once we find that mathematical connection, it's going to be some equation that relates concentration and rate. And that equation is called a rate law. Okay, and that's a nice term, rate law. It's the law that governs the rate. And so if we have some generic reaction where we have A's and B goes to CC plus DD, where the little A's, B's, C's, and D's, that would just be like your balancing coefficients, and the big A's, B's, C's, and D's would be your actual reactants and products there. From that, we can write a general rate law. And this is where we would have rate equals K times the concentration of A raised to some M power times the concentration of B raised to some N power. We have a couple of features here. We've got this little value of K here. K here is a rate constant. It's kind of a variable constant. It's a little bit of a weird term there, rate constant. For a given reaction under the same temperature conditions, that rate will remain constant. If you change the reaction or change the temperature, then the rate constant changes, so it's not very constant. But for a given set of conditions, that rate constant will remain the same. The other thing I want to make sure that I point out is that we've got these rate orders here. That we call them this exponent of m and n. Notice that m and n do not show up anywhere in that balanced reaction. And this is because those exponents are not related to the stoichiometry of the reaction in any way. Now, very frequently, they will equal the numbers for the balanced reaction, or they'll equal the balancing coefficients. That's strictly circumstance. There is no relationship between the balancing coefficients and the coefficients in a rate law. So you cannot write a rate law with values all the way through just from a balanced reaction. So those exponents that we have there are things that are called reactants orders. Okay, so orders in the rate law. Let's talk about these reaction orders. So we mentioned those exponents there. If we wanted to say what is the overall order of the reaction, we would just sum those exponents together. So m plus n, it's not really something that comes up very often, but you just need to know that sometimes that people do that. So how do we find those values of m and n if they're not related to the coefficients of a balanced reaction? Well, we need to do some experimentation. We need to do things that are called rate law experiments, and we'll talk about those. Got a little bit ahead of myself there on the bullet. So let's look at rate law experiments. So rate law experiments are actually a series of experiments that you need to do to see what effect does the reactant have, a given reactant have on a reaction rate. And once you can determine that effect on the rate, you can calculate what the rate law exponent for that reactant is going to be. But notice I have series of experiments. You cannot just do one single experiment and find those rate laws. You need to do a series of experiments. The number of experiments that you have to do is going to depend on how many reactants you have. You have to do at least one more experiment than reactants. So if you have 2 reactants, you have to do at least 3 experiments. If you have 3 reactants, you have to do at least 4 experiments. If you have just 1 reactant, then you have to do at least 2 experiments. And the way I like to think about it is you got to do one to set a baseline, and then you have to do at least one to change each one of the reactants to see what effect it has on the rate. So those are our rate law experiments. So let's look at a particular reaction where we have mercury 2 chloride, HgCl2, and the oxalate ion. Those react together to give us a couple chloride ions, some CO2 gas, and some mercury 1 chloride there. So we have a little bit of a redox reaction going on there. That's not terribly important. We can write a general rate law. So a general rate law is where we don't know the exponents, and so we have our exponents here, m and n. You can call them whatever you want. You can use x and y, p and q. You can make up symbols if you want and give them names. Fred and Barney from the Flintstones. It doesn't matter. They're just variables in there. All right, so here is our series of rate law experiments, and this is generally the way that you would be given data for this type of a problem. So you'd be given all of the experiments, you'd be given the initial concentrations of the various reactants for each experiment, and then you'll be given the rate, the initial rate of that experiment for those concentrations, so that you can calculate the exponents for a change in each one of those. So how do we do that? Well, what we want to do is we want to compare two experiments, and only two at a time. And we want to choose two experiments where only one concentration is changing. That way, if the reaction rate changes, we know which reactant had that effect. If we choose two experiments where the concentrations of more than one reactant is changing, then if there's a change in the reaction rate, we don't know if only one of those reactants had an effect on the reaction rate or if they both did. And so you always want to keep one of your reactant concentrations the same and then only allow one of those to change. And then what you're going to do is from the two experiments that you've chosen, you want to look at the rates. And so what you do is you find the experiment that has the faster rate and you plug that rate in right there, and you put the corresponding concentration for the reactant that you're looking for in there. You take the slow rate, you put it down here in the denominator, and do the same for the corresponding reactant that you're trying to find the exponent for down there. And notice that we've got the ratio of rate fast over rate slow is going to be equal to the ratio of the concentrations fast over slow, and that ratio of the concentrations is raised to some x. And the x value that you solve for there is going to give you your rate law exponent for that reactant. It's a very handy equation. It's nice and compact to use, not difficult at all. I think I may have that one solved on YouTube. If I do, I'll make sure to put a link to that so that you can see how that works out. Now, the other thing that we can do with our rate laws is we might want to plot how they respond over time. And what that does is allows us to determine a concentration of any reactant or of any product at any time during a reaction, a very specific time. So it relates that concentration to time. And the rate law equation is dependent on the overall order of the reaction, whether it's zero order, first order, or second order. And those are the only ones that we're going to look at. So let's look at first order reactions. Initially, they are probably one of the most common type of reactions that we see. And during a first order reaction, the reaction rate of the reaction is directly proportional to the concentration of the reactant involved in the rate law. And when we look at that, we have negative delta R over delta T is equal to K times R. Now what this really is, when we have the change in concentration of R over the change in time, this is really just the rate. So we could write rate equals K times concentration of R. Those two equations right there are exactly the same. Now we can transform that into the integrated rate law using some calculus. And for right now, we're just going to do a little magic. Ooh, look at that. We got natural log of R at time t over concentration of R at time 0 is equal to negative KT. We can do a little bit of calculus here and transform it again. What are those little zeros and t's there? Sorry, my arrows didn't line up for some reason. So we see that concentration of R at 0, that means at a time of 0. That means that's my initial concentration. That's what I started with. And then the concentration of R at time t, so I must have taken a concentration at some time during the reaction, and the t that's here represents the amount of time, that path that you're going to use there in that equation. So that's the concentration of R at the time that you're going to use in that equation. Now, how did we get from here down to here? Well, like I said, we use a little calculus doing that. I do have that derivation published, and I will put a link to that to the YouTube video that shows how you get from that delta R over delta T equals KR down to the log form of that equation. The other thing that we can do is we can plot that equation, and we can put it into a linear form as we see in that graph below. The other thing to kind of take a look at, we see that our slope there is negative. Why does that have a negative slope? It's a very common question. Well, we see that we've got R at time t over R at time 0. Since R is the concentration of a reactant initially, and then we have R at time t is sometime later, well, because R is a reactant, its concentration is always going to be going down because we're turning reactant into product. So the ratio of R at time t over R at time 0 will always be a value less than 1 because R at times t will always be smaller than the initial value. So if you take the natural log of a number that's less than 1, that whole term there is always going to be negative. And so that's why we have this negative term right here. Okay, it all falls out quite nicely in the calculus there. So if we know K, which we can find lots of different ways, we haven't really talked about ways to do that, but there's lots of ways to find the value of K. And we know a time and we know an initial concentration. We can figure out how much reactant should be left over at a certain time, or we can calculate how much product should have formed at a certain time based on the stoichiometry between the reactant and the product. So it becomes a very useful equation there, a very useful graph. What we see there also is that K is independent of concentration. Notice that no matter what my concentration is in here, I have a consistent slope, which is very nice. So the units for K here are inverse time. But first order reactions are very well behaved because that rate constant K is independent of concentration. For second order reactions, they're not quite as well behaved. So this means that your overall order of the reaction is second order. Now, something can be second order in two different ways. It can be second order in one reactant. In other words, it has a squared exponent. Or it can be first order in two reactants. In other words, it can be first order in two different reactants. We're only going to look at the integrated rate form where it's second order in one reactant. If you have two reactants where it's first order, the calculus gets a little bit difficult and goes a little beyond the scope of this course. If you take physical chemistry, that might be something that you explore in that class. So our rate equation here would be negative change in R over change in T is equal to K R squared. And again, all this says is that we have rate, whoops, helps if I have a color. Rate is equal to K concentration of R squared. Okay, so that's all that is. Remember that delta R over delta T is just rate. Okay, we do the integrated form, little magic there, and we have our integrated form there. We have 1 over concentration of R at time t minus 1 over R at time 0 is equal to KT, or we can rearrange that into a linear form as well, where we have something that looks like y is equal to mx plus b. And so that tells us what we would need to plot on our y and our x axes and what else we could find. The units of K here are different. They're liters per mole per time, or it's also inverse molarity time. So you get some really weird units for the rate constant. That's okay. We don't need to worry about that a whole lot. It's just something you need to be aware of if it ever becomes a concern if you're doing some kinetic experiments in the lab. So here's what a second order would look like, where we would plot 1 over a at times t on the y-axis, time on the x-axis, and we get 1 over a0. The original concentration becomes our y-intercept there. We get a positive slope for k here. The one thing that we find is that k actually does change with time, so it becomes a difficult equation to manipulate much further than this. The first order equations we're able to manipulate quite well. And for the second order reaction, I also have the derivation going from the simple differential to the integrated rate form on YouTube. It'll be in the same video as the first order, as is this type, a zero order. Zero order is a very unusual type of reaction where the rate of the reaction is completely independent of the reactant concentrations. This really goes against what we talked about as far as collision theory. It doesn't matter if I have a high concentration or a low concentration of reactant, the reaction rate is exactly the same. This type of reaction actually happens quite frequently if you have a catalyst. And once you've saturated the catalyst, a catalyst surface, if you need the surface of a catalyst for a reaction to take place, once that's saturated, it doesn't matter how much more you have, it can only take place on that surface, and the amount of surface doesn't change no matter how much reactant you put in there. So it is an unusual type of reaction, but they do occur. It's just good to know that they do happen. The rate equation here, we have a negative change in R over delta T. So that's, again, our rate is equal to K times concentration of R raised to the 0 power because it's zero order. And of course, anything raised to the 0 power is 1. So this just becomes 1. And so we end up with rate equals K is our entire rate law. You can integrate that rate equation, and we get R at times t minus R at times 0 is equal to negative kt, or we can rearrange that into a slope-intercept form where we have R at time t is equal to negative kt plus R at times 0. And the units of K are molarity time, molarity times time. So very different units for K depending on the order of the reaction. So now let's take a look at a concept called half-life. So you may have heard the term half-life, and a lot of times it's in regards to radioactive material, but we can also use it in terms of chemical reactions. And believe it or not, the term half-life for these two things means exactly the same thing. When we're looking at half-life for radioactive material, it's the time it takes for half of that material to undergo a radioactive decay. And in terms of reactions, it's the time it takes for the reactants to reduce their concentration by half of where they started at, where you started taking that time. Now we give half-life a time symbol, so T, and then we give it its own special little subscript there, 1/2, to indicate that it's the time to reduce the concentration by 1/2. So a little T 1/2. Now we use half-life primarily for first-order reactions, particularly at this level of chemistry. The reason for that is because the half-life time remains constant during the life of the reaction for first-order reactions. Because of the equations, for 0 and second-order reactions have a variable half-life because they are dependent on the starting concentration, whereas your first-order reactions are independent of starting concentrations. So if you have a graph of concentration versus time, for a first order, you can find the value of the half-life anywhere on that graph. So as I mentioned just a moment ago, we see that half-life is independent of concentration. Zero order and second order are dependent on concentration, and as a result, the half-life changes depending on where you are in the reaction. Now, for a first order reaction, we get that T1 half, so the half-life time is equal to 0.693, which is equal to the natural log of 2. I just went ahead and put it in there as a value, so 0.693, divided by the value of K. And since K is a constant, then the half-life value doesn't change one bit. And since K doesn't change, the half-life doesn't change. So life is really nice with that. Let's see how this works here. So here we've got a reaction starting at 1 molar up here. And let's say that if we want to reduce our concentration by a half, we've got to go to 0.5. How long did that take? Well, we come over here, and at 0.5, it took this long. It took 100 seconds. So that means that my half-life is now 100 seconds. Okay. If I look at, okay, so from 0.5, how long does it take to get to 0.25? Well, I've got to go down to 0.25 because that reduces concentration in half. And so, hey, look at that. It took another 100 seconds. So it's going to take me 100 seconds to reduce concentration by half every time. I don't have to go at the start and at the quarter or anything like that. Let's just start with 0.75 here. It's not very well defined. So 0.75 took me about, I don't know, 30 seconds. So from 0.75, I want to go to 0.375. That's halfway. That's going to be right here. So we'll come over here to this one, and I come down, and look at that. The difference between here and here is also 100 seconds. I can pick any two values on this graph and cut that concentration in half, and it will take 100 seconds, no matter what that starting concentration is. And again, that's what makes the first order reactions so nice. You can't do that with zero order or second order because they're just messier. So here's an example that I think I've got worked out on YouTube as well. So for the decomposition of N2O5, the rate constant K is 1.7 times 10 to the minus 3. We want to know how long will it take for a sample to decompose to 12.5% of its original value. And we've got our reaction right down there. We've got our value for K. Throwing a little bit of a curveball in there because we want to know how long it's going to take to get to 12.5% of its original value. Again, give it a shot on your own. And if you can't get it, go check the solution. All right. If you've got any questions on this content, which is actually a little bit of difficult content in here, make sure you go through it, take a look at the book, email me, come see me, check with your tutor, but make sure that you understand this content. And yeah, look forward to having you watch the next installment of Lecture 3.